Deep inside a high-field MRI scanner with a superconducting magnet, coils are maintained at only about 4 Kelvin above absolute zero. That is close to -269 degrees Celsius, an extremely cold environment created inside a hospital to detect signals from a living body at roughly 37 degrees Celsius. But that enormous magnet does not directly take a picture. MRI does not use X-rays, and it has no light sensor that can see through the body. What it actually measures is an extremely weak electromagnetic response associated with hydrogen nuclei in the water and fat of human tissue. The problem is that an enormous number of hydrogen nuclei at countless locations can all contribute to the signal detected by the receive coil. Once those contributions are mixed together, how can the machine know which part came from the brain, which part came from muscle, and which part came from fluid? The secret of MRI is not simply generating a signal. It is giving that signal a spatial address before reconstructing it as an image. From the outside, an MRI scanner looks like a large tunnel with a patient table that slides into its center. Beneath the outer shell, however, several cylindrical systems are nested inside one another. The deepest layer is the main magnet, which produces a static magnetic field called B0. Many clinical MRI systems operate at 1.5 or 3 Tesla. In common high-field scanners, the magnet coils operate in a superconducting state and are cooled by a cryogenic system containing liquid helium. As long as the superconducting conditions are maintained, the coil has zero direct current resistance in principle, allowing the current to sustain a powerful and highly stable magnetic field. Next are the gradient coils, arranged as 3 sets corresponding to the 3 spatial axes. They do not replace the main magnet. Instead, they create small, controlled variations on top of the main B0 field. Closer to the patient is the radiofrequency system, usually shortened to RF. Depending on the configuration, RF coils transmit electromagnetic pulses into the body, receive the returning response, or perform one of those 2 functions. The main target of this entire system is hydrogen. The body contains large amounts of water and fat, so hydrogen is abundant. The nucleus of the most common hydrogen isotope consists of a single proton and has a magnetic moment. It can be imagined as a tiny quantum compass, although that picture is only a simplification. Without a strong external field, these magnetic moments do not produce a significant net direction. When the body is placed inside B0, a very small imbalance between energy states produces a net magnetization along the main field. At the same time, the protons precess around the field axis at a frequency that depends on magnetic field strength. The scanner has now created the conditions needed to produce a measurable response, but it still has no image, and it still does not know where any part of that response originated. The first enemy is non-uniformity. MRI depends on the relationship between field strength and precession frequency. If B0 varies unexpectedly because of the environment, nearby materials, or the patient's own body, the frequency shifts with it. Even a small deviation can misplace signal or create image artifacts. The system therefore corrects field uniformity through a process called shimming. The second enemy is the energy stored in the superconducting magnet. If one region of a coil heats up and loses superconductivity, electrical resistance appears. That resistance produces more heat, allowing the non-superconducting region to spread rapidly. This event is called a quench. The liquid helium boils rapidly, and the expanding gas must be routed outside through a dedicated vent. A quench reveals that extreme cold is not a secondary detail. It is part of the operating condition that keeps the magnet stable, but the most difficult obstacle to image formation has still not been solved. After a region of tissue is excited, the receive coil does not listen to each proton separately. It detects a combined response from many locations, with all of those contributions overlapping. Imagine a stadium where thousands of people are singing at once. A microphone in the middle records only a mixture of voices. If you want to know where each group is sitting, volume alone is not enough. Each location must leave a distinct signature in the sound. MRI does exactly that by converting position into frequency and phase. But to understand how, we first need to see how the measurable signal is produced. An RF transmit coil sends an electromagnetic pulse. Near the resonance frequency of the protons, the pulse transfers energy into the spin system and tips the net magnetization away from its equilibrium direction along B0. When the pulse ends, the system begins returning toward equilibrium. The rotating and decaying transverse magnetization induces a changing voltage in the receive coil. That voltage is the signal measured by the scanner. The return to equilibrium does not occur in the same way in every tissue. The component along B0 recovers with the characteristic called T1. The coherence of the transverse component decays with the characteristic called T2. Proton density and these relaxation properties vary with the molecular environment. By controlling when pulses are transmitted and when signals are measured, pulse sequences can create different contrasts among fat, muscle, fluid, and other tissues. T1 and T2 help distinguish tissue properties, but they do not reveal location. For that, the scanner must perform 3 encoding tasks. The first is slice selection. When a gradient is applied along one direction, magnetic field strength changes with position along that axis. Because resonance frequency depends on field strength, different positions now have different resonance frequencies. An RF pulse with the selected frequency range excites only the corresponding region. This allows the scanner to select a slice, instead of exciting the entire volume in the same way. 2 dimensions within that slice still need to be localized. Along one dimension, phase encoding gradient is applied briefly. While it is active, protons at different positions accumulate different phase shifts. The gradient then turns off, but the relative phase signature remains encoded in the signal. Along the other dimension, a frequency encoding gradient is applied while the signal is being recorded. It makes signal frequency vary with position. The receive coil still detects a mixture, but that mixture now contains spatial labels. One dimension is distinguished by frequency and the other by phase. The measurement must be repeated with many phase encoding values. Each repetition adds another portion of data to a matrix called K-space. This is not a blurred picture, and an individual point in K-space does not correspond directly to one point in the body. K-space stores the spatial frequency components of the entire image. The region near the center of K-space strongly influences overall image contrast. Regions farther from the center contribute more to boundaries and fine detail. Once enough data have been collected, a Fourier transform separates the mixture of frequencies and phases, then maps that information back to locations in image space. This is the central mechanism of MRI. Gradients convert coordinates into signatures within a signal, and mathematics converts those signatures back into coordinates. The entire machine can now be assembled into a single operating sequence. The main magnet produces a stable, uniform B0 field that establishes net magnetization inside the body. Shimming reduces unwanted field variations. The RF transmit coil drives the spin system away from equilibrium. Gradients select a slice, encode phase, and encode frequency. The receive coil records the voltage induced by the changing transverse magnetization. A computer places the measurements into K-space and uses reconstruction algorithms to create a matrix of image pixels. 3 components must work in precise coordination: the static B0 field, the RF field, and the time-varying gradient fields. B0 creates the conditions for resonance. The RF pulse excites the spin system, the receive coil detects its response, and the gradients attach a spatial address to that response. That coordination also explains the scanner's characteristic knocking sounds. Electric current changes rapidly inside gradient coils positioned within the powerful main field. The resulting time-varying Lorentz forces make the gradient structure vibrate, producing different sound patterns for different pulse sequences. The noise is not the sound of protons, and it is not the main magnet being switched on and off repeatedly. The entire process also depends on the patient remaining still. K-space data are collected through multiple encoding steps at different moments. If anatomy changes position between those steps, the measurements no longer describe the same spatial arrangement. During reconstruction, that inconsistency can appear as blur, ghosting, or other image artifacts. The original obstacle has now been overcome. MRI does not need to isolate each proton, and it does not need a separate sensor at every point inside the body. Instead, it deliberately changes the magnetic field so that location writes its own signature into the combined signal. MRI does not look directly inside the body. It creates a precisely controlled electromagnetic experiment. The main magnet establishes net magnetization within the hydrogen-proton system. RF pulses move that system away from equilibrium. Relaxation properties create contrast between tissues. Gradients encode position through frequency and phase. Finally, Fourier transform reconstructs the encoded data as an image. MRI's greatest achievement is therefore not just a powerful magnet or an extremely cold environment. It is the ability to make quantum physics, superconducting engineering, RF electronics, gradient control, and signal processing operate as a single system, turning an invisible response from the living body into an anatomical map that physicians can use.